Nanochemistry is the field that is an integral part of chemistry, nanoscience, and nanotechnology. Now you may wonder, how does nanochemistry differ from our conventional understanding of chemistry? Well, the answer lies in the scale and the unique properties that emerge at the nanoscale. While conventional chemistry concerns itself with reactions that happen between atoms and changes in their structure, nanochemistry goes a step further. It's all about control and placement of individual atoms or molecules into structures to create materials and systems with new characteristics. Think about it. We're not just observing or initiating reactions anymore. We're actually controlling where each atom or molecule goes. That's the power of nanochemistry. It enables us to understand and control the building blocks of matter at an incredibly tiny scale. But why does this matter? It matters because the small scale of nanomaterials can provide significant improvements in material performance compared to their macro-scale counterparts. This has wide-ranging applications, from creating more efficient energy sources to developing targeted drug delivery systems and even in environmental conservation efforts. Nanochemistry, therefore, plays a unique role in understanding and manipulating matter at the nanoscale. It is the key to unlocking the vast potential of nanotechnology and to harnessing the power of atoms and molecules to serve our purposes. So as we delve into the world of nanochemistry, remember this: it's not just chemistry reduced in size, but a whole new world of opportunities and possibilities. Nanochemistry, therefore, is the chemistry of the future, operating at a scale that promises exciting and revolutionary advancements. To understand nanochemistry, it's crucial to grasp its theoretical foundations. Our journey begins with quantum mechanics, the cornerstone of nanochemistry. This theory, which governs the behavior of particles at the nanoscale, is vital for understanding the unique properties and behaviors of nanomaterials. From the uncertainty principle to wave-particle duality, quantum mechanics provides the language we need to describe the nanoworld. Next, we turn our attention to chemical bonding, molecular orbitals, and electronic states at the nanoscale. The interactions between atoms and molecules give rise to bonds, and these bonds form the backbone of all matter, including nanomaterials. Molecular orbitals, which are regions in space where electrons are likely to be found, play a key role in determining the properties of nanomaterials. At the nanoscale, the behavior of these electrons can lead to fascinating phenomena, such as superconductivity and quantum tunneling. Surface chemistry is another important aspect of nanochemistry. As we shrink materials down to the nanoscale, the ratio of surface atoms to interior atoms increases dramatically. This means surface phenomena such as adsorption, catalysis, and surface tension become increasingly important. Nanostructured materials with their large surface area are particularly sensitive to these surface effects. A good grasp of these theories allows us to predict and manipulate the behavior of matter at the nanoscale. Quantum mechanics helps us understand why nanoscale materials have unique optical, electrical, and magnetic properties. Knowledge of chemical bonding and molecular orbitals allows us to design nanomaterials with specific properties, and an understanding of surface chemistry helps us harness the power of nanostructured materials for applications ranging from catalysis to drug delivery. So as we delve deeper into the world of nanochemistry, remember that these theories are our compass, guiding us through the fascinating and often counterintuitive world of the nanoscale. These theories provide the framework for understanding and predicting the behavior of matter at the nanoscale. Creating nanomaterials requires unique chemical synthesis methods. As we delve into the world of nanochemistry, we appreciate the importance of processes such as chemical reduction methods, sol-gel processes, and chemical vapor deposition. Each has its own unique niche in the synthesis of nanomaterials. In chemical reduction, a reducing agent is used to decrease the oxidation state of a metal ion, leading to the formation of nanoparticles. Sol-gel processes, on the other hand, involve the transformation of a solution system from a liquid sol into a solid gel phase. This method is particularly useful for creating ceramic and glass particles at the nanoscale. Then we have chemical vapor deposition, a process that produces high-purity, high-performance solid materials under a vapor phase at elevated temperatures. But how do we control the size, shape, and functionality of these nanoparticles? This is where precursors, stabilizing agents, and reaction conditions come into play. Precursors provide the necessary atoms for nanoparticle formation. Stabilizing agents prevent the nanoparticles from aggregating, maintaining their size and shape. And the reaction conditions, such as temperature and pressure, can be finely adjusted to control the growth and properties of the nanoparticles. Strategies for synthesizing nanostructures with specific chemical compositions and architectures are also crucial. By selecting suitable precursors and carefully controlling the reaction conditions, we can design nanoparticles with desired properties for specific applications. These methods and strategies allow scientists to create nanoparticles with a high degree of control over their properties. Nanomaterials exhibit fascinating chemical properties that set them apart. When we shrink materials down to the nanoscale, we see a dramatic change in how they behave. Their chemical reactivity, for instance, can increase significantly. This is because at the nanoscale, a larger proportion of atoms are found on the surface of the material, exposed and ready to react. Catalytic activity, too, is influenced by these nanoscale dimensions. Nanoparticles, with their greater surface area compared to their volume, often serve as efficient catalysts, speeding up chemical reactions without being consumed in the process. Let's not forget the photophysical properties. Many nanomaterials show unique light absorption and emission behaviors. Some even change color depending on their size, a phenomenon known as quantum size effect. Speaking of quantum, the quantum confinement effect is another key player here. It refers to how electrons behave when their motion is confined within a space small enough to be influenced by quantum mechanics. This effect can significantly alter the electronic and optical properties of nanomaterials, leading to new possibilities in electronics and photonics. Lastly, surface effects. At the nanoscale, surface atoms dominate and they behave differently than those inside the material. This results in different physical and chemical properties, influencing everything from electrical conductivity to chemical reactivity. These unique properties make nanomaterials highly useful and versatile in a multitude of applications. From electronics to medicine, energy storage to environmental remediation, the potential of nanomaterials is truly vast and exciting. One of the most exciting aspects of nanochemistry is its role in self-assembly and molecular recognition. Now, what exactly does that mean? Let's break it down. Self-assembly is a process by which molecules and nanoparticles spontaneously organize into structured, ordered arrangements. Imagine a group of dancers moving together in harmony without the need for a choreographer. That's what's happening at the nanoscale. This isn't random, though. It's a result of specific molecular interactions and forces, such as hydrogen bonding, van der Waals forces, and electrostatic interactions. On the other hand, molecular recognition involves the specific interaction between two or more molecules through non-covalent bonding. It's like a lock-and-key model, where a molecule, the key, fits precisely into another molecule, the lock. This is fundamental in many biological processes, like the interaction between an enzyme and its substrate. Now, you may ask, why are these processes so crucial in nanochemistry? Well, self-assembly and molecular recognition serve as fundamental strategies to design and produce complex nanostructures with specific functions. For instance, in the realm of DNA nanotechnology, scientists use the principles of self-assembly and molecular recognition to construct intricate nanostructures. Here, the ability of DNA strands to recognize and pair with their complementary strands is harnessed to create a variety of shapes and patterns at the nanoscale. In another example, host-guest chemistry, a subset of supramolecular chemistry, utilizes molecular recognition to create complex structures. The host molecule provides a suitable environment for the guest molecule, resulting in a unique assembly with interesting properties. These processes open up a world of possibilities for creating materials with precise structures and functionalities. The ability to control and manipulate matter at the nanoscale through self-assembly and molecular recognition is a powerful tool, providing the foundation for advancements in areas like drug delivery, sensor technology, and energy storage, These processes are key to designing and creating complex nanostructures with specific functions. As we continue to explore and understand these principles, who knows what incredible nano-sized wonders we'll be able to construct next? Chemistry is the key to creating functional nanomaterials for specific applications. That's the thought that fuels the innovative field of nanochemistry today. But what does it mean to create functional nanomaterials, and how does chemistry fit into this process? Well, the process begins with design and synthesis. Scientists start by envisioning what they want the nanomaterial to do. Whether it's detecting specific molecules, delivering drugs to specific cells, or converting sunlight into electricity, this desired functionality guides the design of the nanomaterial from its size and shape to its chemical composition. Next comes the synthesis part. Here, scientists use various chemical reactions to transform raw materials into nanoparticles with the desired properties. This could involve techniques like chemical reduction, sol-gel processes, or chemical vapor deposition. The choice of precursors, stabilizing agents, and reaction conditions can all influence the resulting nanoparticle's size, shape, and functionality. But the work doesn't stop there. Often, the synthesized nanomaterials need further chemical modifications to fine-tune their properties and functionalities. This could involve attaching specific molecules to the nanoparticle's surface or altering their charge to make them interact with other substances in specific ways. For example, in the field of drug delivery, scientists can modify nanoparticles to carry drugs and release them only when they reach targeted cells. This can improve the effectiveness of the drugs and reduce their side effects. Another exciting application of functional nanomaterials is in the field of sensors. Scientists can engineer nanoparticles to change color or emit light when they come into contact with specific molecules. This can be used to detect pollutants in the environment or disease markers in the human body. Each of these examples represents a case study in the development of chemically engineered nanomaterials with innovative applications. They showcase the power of chemistry in manipulating matter at the nanoscale to create materials with functionalities that were unthinkable just a few decades ago. The potential applications for these functional nanomaterials are vast and exciting. As we continue to explore the possibilities, it becomes increasingly clear that the key to unlocking the full potential of nanotechnology lies in the hands of chemists. Nanochemistry holds great promise for tackling some of our biggest energy and environmental challenges. Let's start with renewable energy. Nanochemistry plays a pivotal role in enhancing the efficiency of solar cells and fuel cells. By manipulating matter at the nanoscale, we can engineer solar cells that absorb more light and convert it into electricity more efficiently. Similarly, in fuel cells, nanochemical modifications can improve the speed of electron transfer, boosting the production of electricity. Now let's talk about the environment. Nanochemistry offers innovative solutions for environmental monitoring and remediation. Chemical sensors, for instance, can be designed at the nanoscale to detect pollutants with higher sensitivity and specificity. By detecting harmful substances at lower concentrations, these sensors can help us monitor environmental conditions more accurately and respond more quickly to potential threats. Nanocatalysts also hold immense potential for environmental remediation. These tiny particles can speed up chemical reactions that break down pollutants, making them an effective tool for cleaning up contaminated air, water, and soil. The beauty of these nanocatalysts is in their size. Their large surface area-to-volume ratio means they can interact with more pollutant molecules, increasing the speed and efficiency of the cleanup process. As we continue to explore the potential of nanochemistry, it's clear that these nanoscale approaches hold significant promise. From harnessing the power of the sun more efficiently to cleaning up our environment, nanochemistry is poised to make a big impact. These nanochemical approaches could revolutionize our approach to energy and environmental sustainability. Though nanochemistry offers exciting possibilities, it also brings challenges and ethical considerations. As we plunge into the realm of the infinitesimally small, the challenges of reproducibility and scalability become more pronounced. At the nanoscale, minor variations in experimental conditions can lead to significant differences in outcomes, making it difficult to consistently reproduce results. Scaling up these processes from the lab to industry is another hurdle. The techniques that work on a small scale may not be economically or technically feasible on a larger scale. Safety is another major concern. Nanoparticles can have drastically different properties than their bulk counterparts, and their impacts on human health and the environment are not yet fully understood. Extensive research and rigorous testing are needed to ensure that nanomaterials are safe to use and handle. On the ethical front, the potential implications of nanochemistry on society cannot be ignored. As with any disruptive technology, the benefits of nanochemistry must be balanced against potential drawbacks, such as issues of privacy, equity, and access. Lastly, the rapid advancement in nanochemistry underscores the need for responsible research. Regulatory frameworks must evolve to keep pace with the technology, guiding its development in a manner that is ethical, safe, and beneficial for all of society. Addressing these challenges is crucial for the responsible and sustainable development of nanochemistry. The future of nanochemistry is rich with potential. As we look ahead, we see emerging trends such as the development of advanced nanomaterials and the convergence of nanochemistry with quantum computing. We also anticipate potential breakthroughs in the synthesis of nanostructures with unprecedented precision and control. Future directions may include exploring new realms of chemical reactivity at the nanoscale and expanding the application of nanochemical principles in energy, medicine, and environmental science. The future of nanochemistry promises to be as exciting as it is challenging. Nanochemistry is a field that invites curiosity and exploration. The fascinating world of atoms and molecules at the nanoscale is full of surprises and challenges. It's a realm where conventional chemical rules are rewritten, where properties and behaviors shift dramatically, and where innovative applications become possible. This complex field offers countless opportunities for questions and discussions. How does the chemical nature of nanoscale materials influence their properties? How can we manipulate these properties for specific applications? What are the challenges and ethical considerations in advancing nanochemical technologies? These are but a few of the intriguing queries that nanochemistry presents. The exciting journey of nanochemistry is far from over. New methods are being developed, new materials are being synthesized, and new applications are being discovered. As we continue to explore this frontier, we are constantly reminded of the immense potential that lies within the nanoscale world. As we conclude, remember that nanochemistry is a rapidly evolving field that holds the key to many technological advancements of the future.